In set theory, a null set NR is a set that can be covered by a countable union of intervals of arbitrarily small total length. The notion of null set in set theory anticipates the development of Lebesgue measure, since a null set necessarily has measure 0. Definition: suppose A is a subset of the real line R such that where the unner intervals of U is the length of U, then A is a null set. In terminology of mathematical analysis, this definition requires that there be a sequence of open covers of A for which the limit of the lengths of the covers is 0. Null sets include all finite sets, all countable sets, and even some uncountable sets such as the Cantor set. Properties: the empty set is always a null set. More generally, any countable union of null sets is null. Any measurable subset of a null set is itself a null set. Together, these facts show that the M null sets of X form a sigma ideal on X. Similarly, the measurable M null sets form a sigma ideal of the sigma algebra of measurable sets. Thus, null sets may be interpreted as negligible sets, defining a notion of almost everywhere. Lebesgue measure. The Lebesgue measure is the standard way of assigning a length, area or volume to subsets of Euclidean space. A subset N of R has null Lebesgue measure and is considered to be a null set in R if and only if, given any positive number epsilon, there is a sequence in of intervals in R such that N is contained in the union of the in, and the total length of the union is less than epsilon. This condition can be generalized to Rn, using n cubes instead of intervals. In fact, the idea can be made to make sense on any differentiable manifold, even if there is no Lebesgue measure there. For instance, with respect to Rn, all one-point sets are null, and therefore all countable sets are null. In particular, the set Q of rational numbers is a null set, despite being dense in R. The standard construction of the Cantor set is an example of a null uncountable set in R. However, other constructions are possible which assign the Cantor set any measure whatsoever. All the subsets of Rn whose dimension is smaller than n have null Lebesgue measure in Rn. For instance, straight lines or circles are null sets in R2. Sard's lemma. The set of critical values of a smooth function has measure 0. If lambda is Lebesgue measure for R and pi is Lebesgue measure for R2, then the product measure lambda x lambda equals pi. In terms of null sets, the following equivalence has been styled a Fubini's theorem. For AR2 in uses null sets play a key role in the definition of the Lebesgue integral. If functions f and g are equal except on a null set, then f is integrable if and only if g is, and their integrals are equal. A measure in which all subsets of null sets are measurable is complete. Any non-complete measure can be completed to form a complete measure by asserting that subsets of null sets have measure 0. Lebesgue measure is an example of a complete measure. In some constructions, it's defined as the completion of a non-complete Borel measure. A subset of the Cantor set which is not Borel measurable. The Borel measure is not complete. One simple construction is to start with the standard Cantor set K, which is closed, hence Borel measurable, and which has measure 0, and to find a subset f of K which is not Borel measurable. First, we have to know that every set of positive measure contains a non-measurable subset. Let f be the Cantor function, a continuous function which is locally constant on Kc, and monotonically increasing on 0, 1, with f equals 0 and f equals 1. Obviously, f is countable, since it contains 1 point per component of Kc. Hence f has measure 0, so f has measure 1. We need a strictly monotonic function, so consider g equals f plus x. Since G is strictly monotonic and continuous, it is a homeomorphism. Furthermore, G has measure 1. Let EG be non-measurable, and let F equals G minus 1. Because G is injective, we have that Fk, and so F is a null set. However, if it were Borel measurable, then G would also be Borel measurable. Equals -1 is the pre-image of f through the continuous function h equals G minus 1. Therefore, f is a null, but non-Borel measurable set. Null. In a separable Banach space, the group operation moves any subset AX to the translates A plus X for any XX. When there is a probability measure mu on the sigma algebra of Borel subsets of X, such that for all X, mu equals 0, then A is a null set. The term refers to the null invariance of the measures of translates, associating it with the complete invariance found with measure. Some algebraic properties of topological groups have been related to the size of subsets and null sets. Null sets have been used in Polish groups to show that when A is not a megaset, then A1A contains the identity element. This property is named for Hugo Steinhaus since it is the conclusion of the Steinhaus theorem.